In the mid-1950s, an engineer at the Euclid division of General Motors looked at a problem that had frustrated equipment builders for years and arrived at a solution nobody else had managed to make work. Contractors needed more pushing power than a single diesel engine could deliver. But every attempt to simply bolt two machines together had produced something clumsy, rigid, and prone to tearing itself apart on uneven ground. Euclid's answer was the TC-12, and it did not just solve the problem. It became, for a brief window in industrial history, the most powerful crawler tractor in the world. That demand for raw pushing power did not come from nowhere. The 1950s were the opening years of the largest public works effort the United States had ever undertaken. The Federal Aid Highway Act of 1956 authorized the construction of the Interstate highway system, a project that would eventually require cutting, grading, and moving earth across tens of thousands of miles of new roadway. At the same time, the country was in the middle of an equally massive era of dam construction, building hydroelectric and flood control projects that required enormous, sustained earth moving on a scale ordinary contractors had rarely faced before. Both kinds of projects shared the same basic problem: an enormous, continuous volume of earth that needed to be pushed, graded, and shaped, often in remote locations where bringing in multiple separate machines was less efficient than concentrating raw power into fewer, larger units. A single crawler tractor with double the horsepower of anything else available was not a novelty in this environment. It was a direct answer to exactly the kind of job the country was building by the thousands. To understand why building that machine was difficult, you have to understand what every earlier attempt had gotten wrong. The idea of combining two engines into one crawler tractor was not new when Euclid took it on. Contractors and smaller manufacturers had experimented with the concept since the 1940s, most commonly by taking two complete machines, like a pair of Caterpillar D8s or Allis-Chalmers HD19s, and physically joining them end-to-end or side-by-side. These conversions worked, in the sense that they produced more horsepower than a single machine could offer. But they were built as afterthoughts, retrofitted onto equipment that had never been engineered to share a single, unified structure. The resulting machines were rigid, heavy, and mechanically fragile, because a crawler tractor's undercarriage is designed to flex slightly as it crosses uneven ground, and two rigidly joined machines could not flex independently of each other. On rough terrain, that rigidity translated directly into stress on the frame, the tracks, and the drivetrain, stress the original single-engine design was never built to absorb. Euclid's engineers did not try to join two existing machines. They designed the TC-12 from a blank sheet, specifically to carry the output and the weight of two complete powertrains. Each engine and each transmission was mounted on its own independent chassis, essentially two separate half-tractors, rather than being crammed onto a single shared frame. Those two chassis were then connected by a crossbeam, engineered specifically to allow them to oscillate against each other as the machine crossed rough ground. When one track dropped into a depression, that side of the machine could pivot slightly at the crossbeam connection without transmitting the full mechanical shock into the opposite track or into the frame carrying the second engine. It was a small structural decision, but it was the detail that separated the TC-12 from every earlier attempt at a twin-engine crawler. The machine was allowed to bend, just slightly, exactly where it needed to. Inside each half of that split frame sat a General Motors 671 diesel engine, and the choice of that specific engine was not incidental. The 671 was a two-stroke diesel, part of a Detroit diesel engine family. General Motors had been refining since before the Second World War. Two-stroke diesels fire on every single revolution of the crankshaft, rather than every other revolution the way a four-stroke engine does, which gives them a higher power density for their physical size and weight. For a machine already carrying 2 complete engines, 2 complete transmissions, and 2 complete cooling systems, that compact power-to-weight advantage mattered enormously. A pair of 4-stroke engines with equivalent output would have added substantial extra weight and length to a machine that was already pushing the practical limits of what a crawler undercarriage could support. The trade-off was a 2-stroke engine's higher fuel consumption and a distinctive, aggressive exhaust note operators of the era learned to recognize from a considerable distance long before the machine itself came into view. Each engine drove its own Allison transmission, feeding power directly to the track on its own side of the machine. On later production models, the combined output of both engines reached roughly 450 horsepower, delivered not as a single unified power source but as 2 entirely separate systems, mechanically independent from the crankshaft all the way down to the final drive. That independence turned out to produce a capability nobody had specifically set out to build. Because each track was powered by its own dedicated engine and transmission, an operator could counter-rotate the 2 sides against each other, driving one track forward while running the opposite track in reverse. On a conventional single-engine crawler, this kind of maneuver puts enormous strain on a single central differential or steering clutch system, trying to force one output shaft to do 2 contradictory things at once. On the TC-12, there was no single shaft being asked to contradict itself. Each side simply did what its own engine told it to do. The result was a machine that could rotate almost in place, spinning around its own central axis with a tightness that no comparably sized single-engine tractor could match. For a machine built primarily for brute pushing power, this maneuverability was an unexpected advantage, one that made the TC-12 useful in tight, congested job sites where a conventional crawler this size would have struggled to turn around at all. None of this made the TC-12 an easy machine to operate. A single person sat in the cab, but that person was, in a very real mechanical sense, running 2 separate tractors at once. 2 engines meant 2 throttles to manage, 2 transmissions responding to load independently, 2 sets of gauges to monitor, and 2 entirely separate cooling systems working to keep each engine within its operating temperature. Veteran operators who ran the TC-12 described it less like driving a single oversized machine and more like coordinating 2 machines that happened to share one seat. If one engine's transmission engaged a fraction of a second before the other, the tractor could momentarily crab sideways instead of driving straight, a correction the operator had to feel through the machine and compensate for constantly, rather than something the mechanical system corrected on its own. And the risk was not purely theoretical. If one engine lost power mid-push, whether from overheating, a fuel delivery problem, or a mechanical failure inside the transmission, the operator suddenly had one side of the machine still producing full power while the other side went slack. Left uncorrected, that imbalance would swing the entire tractor hard toward the dead side, potentially driving the working track into an uncontrolled pivot at full load. Experienced operators learned to recognize the earliest signs of one engine falling behind the other, a subtle change in sound or a slight drift in direction, and to back off the throttle immediately, rather than wait for a gauge to confirm what they could already feel through the seat and the controls. The machine's size and weight also meant it rarely traveled far under its own power. Standard lowboy trailers of the era were not built to carry a tractor this heavy, which meant the TC-12 tended to stay wherever it was assigned, moving from one section of a job site to another rather than being routinely transported between distant projects. That limitation shaped where the machine actually ended up working. It found its most consistent use in large-scale, fixed-location projects, dam construction, major highway cuts, and surface mining operations. Environments where a single machine could be positioned once and kept working continuously on enormous volumes of earth, rather than needing the mobility of a smaller, more easily transported dozer. By the time production wound down, Euclid itself had already become something considerably more complicated than the company that had originally designed the TC-12. Euclid began as a family manufacturing business, built by George Armington and his 5 sons. General Motors acquired the company in the early 1950s, which is the ownership era under which the TC-12 was actually developed and released. But Euclid's corporate identity did not stop there. Antitrust pressure eventually forced General Motors to divest the truck side of the business, which passed to White Motor Corporation, then to Daimler-Benz, then to Clark Equipment Company, then to a joint venture known as Volvo Michigan Euclid, and finally to Hitachi, which used the Euclid name briefly to enter the dump truck market before retiring it entirely by 2004. Along the way, some TC-12 units were also sold under the Terex nameplate, another name Euclid's equipment carried during one of these corporate transitions, which is why the same machine occasionally surfaces in old records and surviving examples under 2 completely different brand names. The TC-12 did not remain in production long. Its size, its complexity, and the sheer mechanical overhead of maintaining 2 complete diesel powertrains in a single machine made it a specialized tool rather than a mainstream product, useful in exactly the kind of large, fixed, brute force earth-moving projects it had been built for, and largely impractical anywhere else. Smaller, more efficient single-engine crawlers eventually closed the horsepower gap that had justified building a twin-engine machine in the first place, and the specific engineering problem the TC-12 had been designed to solve simply stopped being a problem worth solving with 2 engines instead of 1. What survives of the TC-12 today exists almost entirely in the hands of collectors and vintage equipment enthusiasts, restored and maintained specifically because the machine represents something genuinely unusual in the history of earth-moving equipment. Not simply a bigger version of an existing design, but a fundamentally different structural answer to the same question every equipment builder was asking in the 1950s. How do you combine more power than a single engine can offer, without combining the fragility that comes with forcing 2 machines to behave as if they were only ever built to be one?